Welcome to the Space Telescope Public Lecture Series. Tonight, Webb's first look, images and spectra from NASA's newest great observatory with Dr. Alexandra Lockwood of the Space Telescope Science Institute. I'm your host. I'm Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And I always thank our amazing tech team, Thomas Marufu and Grant Justice, who record this session and get it out to you on YouTube. I will note that even though the pandemic has died down, the Space Telescope Public Lecture Series will continue to be online only until further notice. Our upcoming lectures in September, First Light, Unveiling the Properties of Galaxies at Cosmic Dawn, from Guido Roberts Borsani at UCLA. That sounds really cool, looking out into space and back into time. On October, we have a very special talk for you, The Universe of Dante Alighieri, by a descendant of Dante Alighieri named Spirello di Sorrego Alighieri. This is going to be really cool, looking at the way astronomy and the universe is put into Dante's works. And November, we have black holes. How do we see that which gives off no light? From Stephanie Lamassa, also here at Space Telescope Science Institute. To find information about these lectures, you can go to our website, www.stsci.edu/public-lectures. And on there, on the left side of the page, as you see, we have our YouTube playlist and our webcast archives that are from those STSCI. And on the right, you see our easy method for subscribing to our email list. Just enter your email address and push the button. Also on our web pages, we have lists of the upcoming lectures. And if you click on one of those lectures to read more, it will give you the information about the speaker and the abstract of the talk, as well as, after it's been recorded, links to the STSCI webcast, as well as the posting on YouTube. About our email is, as I showed you, you can sign up at our website. You can also just subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, and you will get new video notices and reminders of live events such as this. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media channels include Facebook, Twitter, YouTube, and Instagram. We have channels for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute. I myself do a tiny bit of social media. You can find me on Facebook and Twitter as Dr. Frank Summers. And now our news from the universe for August 2022. Now, I know you all are excited to get to the Webb images, so I'm only going to do one story, but it's a really cool little story. I call this story, Where's Waldo? Black Hole Edition. So some of you may remember, a lot of you may remember, the Where's Waldo books, in which you're given a really complex picture like this, and your job is to find this Waldo character in his red and white striped sweater and hat in there. And, you know, it's kind of fun. It's a hunt and search for one character amongst many, and you have to notice all the details and such. By the way, I know some of you are trying to squint at your screen right now. This is where Waldo is in this picture, okay? Now, in the astronomical version of it, we are looking in an image like this, a star field. This is actually a star field toward the galactic center, toward the center of our galaxy, tons and tons and tons of stars. And in this image, we're not looking for Waldo, we're looking for a black hole. Now, there are black holes that are free-floating across our galaxy. And what happens is that when you form a black hole by a supernova explosion, that explosion doesn't have to be symmetrical. It can be asymmetrical and give that black hole a kick and give it a significant motion across the galaxy. So there are, we understand, lots of black holes just floating out amongst the stars. And so now we're going to play a Where's Waldo to try and find that black hole in this image, because it's there. And remember, of course, that black holes emit no light. So how are we going to find a black hole? Well, if you've been paying attention to the news over the past couple of years, you know that we've actually taken a couple pictures of black holes using something called the Event Horizon Telescope. And this is the image of the supermassive black hole in the galaxy Messier 87, M87. Now, this was taken with the Event Horizon Telescope, which is a combination of many radio telescopes across Earth. And this black hole is, as it's described here, supermassive, about 1 billion times the mass of the sun. The black hole we're looking for is not supermassive, and we're using Hubble, which is not a radio telescope. So we can't use this method to find the black hole. Another method that we use to find black holes is when they are in a binary system, and the material from the companion star flows off of the companion star into like a disk around the black hole, and that material gets speeded up to relativistic speeds, emits huge amounts of energy. Sometimes there's jets, and we can see them in X-rays. All right, and so these are called X-ray binaries. Now, again, this black hole we're looking for isn't in a binary system, and we're not using an X-ray telescope, so we can't use this method. The method that we're going to use to find it is a method called gravitational microlensing. All right, and so this is where the gravity of the black hole shows its existence. So in panel 1 on the left here, we have this black hole that's going to pass between a distant star and Earth. It's not passing through, so the image of the star is its normal image, okay? But as a black hole passes directly through, the light from the star gets warped around the black hole. The black hole is a big enough distortion in space-time. It actually warps the light around it and causes the image of the star to brighten. It focuses extra light rays onto us, and so the brightness of the star is amplified. And then, of course, in panel 3, you can see when the black hole goes away, star goes back to being normal. So there is this sequence of brightening and fading that is characteristic to microlensing. And of course, stars vary, they go up and down a lot for many other reasons. So you got to watch it a long time to make sure that it does this pattern and it doesn't repeat it and such. And we've been doing microlensing for many years, and we've seen tens of thousands, somebody said 30,000 events like this, where we've seen microlensing. But we have never seen one that was a black hole microlensing. We saw that one of the things that are other stars passing through, which also can create this microlensing effect. And we know that there are stars because as it passes through, the color of the background star changes a bit. It's added in the color of the star in the foreground. Black hole emits no light, so there would be no color change. And so we did find one in that field that I showed you before, and its catalog number is OGLE-11-462 or OG11-462. And it's this thing right in here. And let me blow this up so you can see what's going on here. So what we have here is a lot of ground-based telescopes doing a lot of searching. And when they find an interesting event, then it triggers Hubble to go into action. So Hubble, in its very first image that we have here in August of 2011, is actually the star here that's pointed to by the arrow is very bright. This is in its amplified state. And then you can see in October 2011 and September 2012, it has decreased. So we catch sort of the second half of the light curve. The ground-based telescopes catch the first half, the Hubble catches the second half, and Hubble's continued to watch it for 6 years, going all the way to August 2017. And you need to do that in order to really make sure the light curve is the way it is. And then also that Hubble can verify that this is a black hole lensing candidate because there is no color added to the light of the background star. You need to get to when you can see the background star in its normal state. So the thing that Hubble can really do that no other telescope can do is measure the precise location of that star. All right. And as the black hole passes in front of it, it actually jitters the star just a tiny bit, right? And so that motion of the star, that jittering of the star back and forth as the black hole passes across is something that Hubble can measure. And when you measure that, you not only can tell, hey, this is a black hole event, but you can also measure the black hole parameters. And the group that did this came up with the black hole was about 7 times the mass of the sun, 7 solar masses, and that it's over 5,000 light years away. All right, so we're watching and we're seeing this floating black hole going across the galaxy, making a random background star brighten, and we'll be able to detect these free-floating black holes traveling throughout our galaxy. So, during the pandemic, Where's Waldo kind of got a lot more easier because if they have to social distance, it's pretty easy to find Waldo. But it's not so easy for astronomers, even if they were socially distant, because remember, astronomers were playing Where's Waldo with an invisible Waldo. All right. Our speaker tonight is Alexandra Lockwood from the Space Telescope Science Institute. Or actually, she was from the Space Telescope Science Institute, but she has now left us. She obviously did such a great job for us that she was stolen by NASA headquarters. She's now working at the, actually, she told me her first day today down at the Science Mission Directorate at NASA HQ, where she has the title of Strategic Content Integrator, and you can ask her what that means at the end of the talk. I'm not sure she knows just yet. She's going to define her own job. But before she left us, she was the project scientist for the Webb Space Telescope outreach here at the Space Telescope Science Institute. She got her bachelor's degree in physics and astronomy from the University of Maryland, and the master's and PhD from Caltech in planetary sciences, where her research focused on understanding planetary systems and characterizing exoplanets. She also, before coming to us, she worked on the Joint Polar Satellite System mission at the King Abdullah University of Science and Technology in Saudi Arabia. She tells us that outside of work, she loves running, yoga, and laughing with her kids. Yes, also in doing all of this, she's also raising a family. So doing a wonderful job at everything. Ladies and gentlemen, Dr. Alex Lockwood.
Wow, what an introduction. Thank you. Frank. Yes, I do have 2 very young kids at home, so I apologize if you hear screams. I promise they're safe. It has been my very, very incredible pleasure to have worked on Webb for the past 5 years, and to really help the mission get to where we are today, which I'm sure you all recognize the image behind me. And today we'll talk a little bit more about the path that led us here, and where we're going from here. So with that, let me share my screen. And hopefully you are seeing the right view. All right, so as Frank said, I'm Dr. Alex Lockwood, and I've spent the past 5 years working on the Webb mission, leading its communications and outreach efforts. And so here we are, almost exactly 1 month after we saw the first images from Webb. And I am elated to say that it was worth the wait. It was everything we hoped it would be. But how did we get here? So we'll talk a little bit about what has happened in the past 6 months since I actually gave a talk on Webb to this same audience. And you can see that talk in the archives if you'd like. where we talked more about the previous steps of the mission, but let's talk about what has happened in the past 6 months to get us from our launch to where we are today. We'll go back and talk about some of the motivations for the telescope, which include studying, the motivations for studying infrared light, what Webb was anticipated to do, and then we'll look at the very first results that clearly showcase that Webb is capable of doing what it was designed to do, and so much more. So I don't know what you all were doing on Christmas morning, but this was a very exciting Christmas for me as we watched the telescope launch on an Ariane 5 at 7:20 in the morning on Christmas morning. It was beautiful. It was an excellent launch with a $10 billion payload. Needless to say, we were holding our breath, but it went off seamlessly, so much so that a few weeks ago, they reported that officially that there is over 20 years of a lifetime, and that number was very much dependent on the precision of the trajectory, both during the launch and in subsequent maneuvers that the telescope made to get into its orbit. But the Ariane 5 rocket provided by the European Space Agency that took Webb off performed beautifully. It was a momentous occasion. I think even more iconic was this beautiful image that was taken as the spacecraft separated from the fairing. You can see the limb of the Earth, and this was a mere seconds before the solar array successfully deployed very quickly and efficiently. And we've had successful power ever since. This was 27 minutes into flight, and at that moment, when the spacecraft separated, the operations of the telescope moved from the launch service provider Arianespace to the Space Telescope Science Institute, where the Mission Operations Center is. So that was a big moment, and the Space Telescope Science Institute has been operating Webb ever since, both in mission and in science operations. Shortly thereafter, this beautiful launch came a very harrowing few weeks of unfolding. In order to get this behemoth of an observatory, and we'll talk about why it has to be such a behemoth, into space, even on the largest rocket available internationally, which was the Ariane 5 at the time, we had to fold it up. And that meant we had to unfold it in space, with both the option of doing it manually and doing it automatically, but from hundreds of thousands of miles away. And so many pieces of these, what we call deployment sequence, had never been done before. Yes, we've put a telescope in space and satellites in space. Yes, we've had communication antenna and solar arrays deploy before successfully many times, but everything else almost was a first time. And within the first 2.5 weeks after Webb was launched, it was beautifully deployed in space, following this sequence where the sun shield opened, making sure to always protect the mirror from the heat of the sun, the Earth, and the moon. The sun shield fully tensioned, the secondary mirror, which is a huge single point of failure, deployed to its position, and the full expanse of the primary mirror wings came out. I'll tell you that this is literally the size of a house on a tennis court, and we unfolded it from hundreds of thousands of miles away. To say it is a feat of engineering is an understatement. This telescope is motivated by its giant mirror and the science requirements therein, or I would say the science desires, the science requirements. But in order to protect this giant mirror, this giant hexagonal gold mirror from the sun, there is a 70-foot sun shield made of hair-thin layers of material that was uniquely designed to create 600 degrees of temperature differential between the two sides of the telescope, but also be extremely thin, lightweight, and foldable. All of this, there's so many new technologies here created to enable Webb. And not only did they work, but they have subsequently been used in a lot of other applications, including not just other astronomy applications, which the infrared detectors were elevated, upgraded, and they have been used subsequently, but also things like laser eye procedures and mammograms. So, these engineering feats that have accomplished just amazing science have also gone on and infiltrated other places in our society as technological advances. None of this would be possible if it weren't for an international collaboration. NASA has recognized that it takes a village, and specifically the Ariane 5 rocket was the only rocket at the time that had a fairing size large enough to hold Webb. And so the European Space Agency contributed the rocket, Arianespace, the launch provider, as well as 1.5 of the scientific instruments, the mid-infrared instrument and the near-spec instrument. The Canadian Space Agency provided the guiding functionality, the fine guidance sensor, and the nearest instrument, which those two pieces are packaged together. So this is a collaboration from NASA, the European Space Agency, and the Canadian Space Agency, including 14 countries that helped to build and develop this telescope. And now that we have scheduled the first year of science on the telescope, this is actually a map showing countries that have been successfully awarded science time in the first year of observations. So you can see that, well, I don't know if you can tell immediately off this map, but there's over 40 countries from which scientists will be using Webb data just in the first year. And that doesn't count all of that's only given proposals. There will be many other people who take the data as it's available online and use it to produce new science. Talk a little bit more about the parts of the observatory. The main part, as I mentioned, is the giant mirror, protected by a 5-layer sun shield made of super thin and very thermally insulating Kapton material. The science instruments are on the back side of the telescope, of the mirrors, and a secondary mirror helps collect and focus the light from the primary mirror, sends it back behind the primary mirror to the science instruments. On the sun-facing side of the observatory, you have the solar panels, communication antenna, which in addition to being solar-facing is also earth-facing at all times. And that's how we get our communications, both uploading and downloading, and as well as steering and control and star trackers. The key to Webb really is its giant mirror. It is over 6 times the area of Hubble's mirror. This is primarily due to the fact that we are working at infrared wavelengths, which we'll talk a little bit more about. And in order to get the same clarity of images, which, as you can see from my background, and if you've seen the images, we do have the same clarity. These images are absolutely stunning. But for longer wavelengths, you need a larger mirror to get that same beautiful clarity. Additionally, if we want to see very faint things, even with the use of gravitational lensing, as Frank had mentioned, we need a bigger photon collector, a bigger bucket to collect our light. And so we needed a bigger mirror. Such a bigger mirror, though, necessitated all of these technological advancements and incredible technology and development and engineering to get it into space, as we've discussed. Also, Webb's mirror is gold. It's only about a golf ball size worth of gold. Only about the mass of a golf ball, size of a golf ball, spread over these 18 mirrors, this 20-foot diameter mirror. Very thin layer, but that's because gold is the most reflective at infrared wavelengths. Hubble is a silver mirror. The mirror in your bathroom is probably also a silver mirror. That's because that's one of the most reflective surfaces at visible wavelengths that our eyes see. So Webb is gold because it's an infrared telescope. There are 4 science instruments on the back of the telescope: near spec, near cam, near-IRIS, and MIRI. The ones that start with NIR are for near infrared, and the one that starts with MIR is a mid-infrared instrument. They all have unique specialties, but they are all kind of multifunctional instruments. So each one of them has an imaging and a spectroscopic capability, all very powerful and offering unique specialties for the variety of science that Webb is going to do. And all of this amazing unfolding and science to happen is happening a million miles away. Webb was put into an orbit much, much, much different from Hubble's. Hubble's in near Earth orbit, a low Earth orbit, which provides its own opportunities and challenges. But Webb was specifically put at a location we call the second Lagrange point. It is a semi-stable gravitational location, orbital location, that simultaneously allows the telescope to always face away from the sun, the earth, and the moon, which are 3 sources of infrared heat that could confuse it, and also simultaneously always face the earth on the sun-facing side so that we always have communications. Additionally, as I mentioned, it is a semi-stable orbital location, so it doesn't require a lot of fuel to stay there. And as I mentioned earlier, thanks to the excellent trajectory given to us by the Ariane 5 rocket and the engineers and the maneuvers that they did in the subsequent weeks after Webb's launch, we have enough fuel to maintain an orbit for 20 years. And given that orbital location and always being able to talk to Earth, we take advantage of the deep space network with locations in Goldstone, California, Madrid, Spain, and Canberra, Australia, to have daily communications, both sending commands and downloading data to the telescope every day of the year. And we technically at any given time have the opportunity to communicate with the telescope if necessary. And as I mentioned, the telescope Mission Operations Center, Webb's Mission Operations Center, is located in Baltimore, Maryland, which doesn't often get the best rep, but surely is a very influential city in that it operates both the Hubble and the Webb Space Telescopes. And the mission operations for the telescope is located in Baltimore. This is an image of the Mission Operations Center on the right-hand side with a very cool Webb astronomy mask. Is the mission operations manager, Carl Starr, who led us through this very intense 6 months commissioning period. All of it went swimmingly, and we are here where we are today. So let's talk more about the science. Webb is a giant infrared telescope, and one could ask, why do infrared instead of, for example, visible? What we can appreciate with our eyes, what Hubble has shown us, is a beautiful view of the universe. Well, infrared is very complementary to visible. For example, you can see here views of 2 different kinds of animals, meerkats and crocodiles. On the left are visible images, and on the right are infrared images. Very complementary, but quite different. The features that you can see, what stands out. And these images really show you the sort of #1 feature of infrared light to us, which is that it's heat. The meerkats, which are warm-blooded animals, glow bright in infrared light. You can see their eye sockets. You can see their warm bellies, very bright in infrared light. And the cold-blooded freshwater crocodile is quite dull. So first and foremost, infrared light is heat. And whether it's the sun, or stars or planets or even interstellar dust. All of these things give off heat signatures that we can study with Webb. Infrared light is longer wavelengths than visible light, which also makes it a very crucial thing, which we'll talk about. And Webb was specifically chosen to study near and mid-infrared wavelengths. We talked about the 4 instruments. 3 of them start with NIR for near, and 1 of them is a mid-infrared instrument. But it was specifically chosen to study those wavelengths for the capabilities, the astronomical insight that they provide. And it happens to also overlap with a little bit with what the Hubble Space Telescope has in terms of capabilities and what the Spectra Space Telescope had in terms of capabilities. And so this both validates the results that Webb will get. You know, it's a good cross-check, but it also means that we can expand upon the findings of Hubble and Spitzer. Spitzer is no longer operational, but it did incredible things to pave the way for Webb, especially in exoplanets. And Hubble is still operational, but doesn't go so far into the near infrared that as much as it used to, and is very complementary to Webb in that Webb has better clarity at near infrared wavelengths and can just provide more details further along the spectrum, literally and figuratively. So at infrared wavelengths, talking about the near and mid infrared wavelengths, they are both complementary to visible wavelengths, but they're also unique in what they show us. Shown here, you can see a visible light image where you have hot clouds of gas coming through, emanating invisible light, very beautiful. But you can also see these dark veins of dust that block a lot of the gas and the light. At near infrared wavelengths, you can start to see through that dust. It is literally like seeing through fog. And when you see through dust, obscuring dust, you can see thousands of stars. So near infrared wavelengths allow us to peer through dust, start to see things we haven't seen. And a lot of times those are stars and young stars that are forming within those clouds of dust. Now, mid-infrared wavelengths are quite different, as you can see, and that's where you're actually studying the dust. So visible wavelengths, you're studying a lot of hot gas, and you see the dust, but it's blocking your knowledge. At near infrared wavelengths, we start to see through the dust and what's behind there to get a picture. And then at mid infrared wavelengths, the dust itself, the warmth of the dust actually starts to shine brightly, and we can understand things like the temperature and physical structure and composition of the dust itself. So all of this is quite complementary when you're talking about an environment that has dust and gas, and you want to study the dust and the gas and where they are and co-spatially located. So Webb does it all. And additionally, maybe more importantly, but I wouldn't order the importance of the science that Webb can do, is looking at the ancient universe, the beginning of the universe. Webb's first motivation was to study the earliest galaxies. And this is possible because the earliest galaxies are very, very, very far away. Their light has been traveling for so long that as the universe expands, the wavelength of light has expanded. And as we were looking at the electromagnetic spectrum earlier, red light or even blue light from distant galaxies, as the universe has expanded, the light itself has expanded, and it's expanded all the way to infrared wavelengths. So Webb is uniquely positioned to study light that has traveled from the beginning of the universe across the distance and time of the expansion of the universe. Webb is the only observatory that can see these objects because their light is at infrared wavelengths. And being so far away, being so distant, they're very faint. It's another reason Webb is so big, is because that big light collecting bucket of a mirror is the only thing that's able to capture these very faint, distant objects. So that's another benefit of infrared wavelengths. The other very cool piece about infrared wavelengths is that it just happens to tune in on some really interesting and incredible molecular information. So we'll talk a little bit more about that. But just an example right here is atomic detections of oxygen, hydrogen, nitrogen, and sulfur that we get at infrared wavelengths, and some that are redshifted into infrared wavelengths that were previously invisible wavelengths, which we've seen now with the first galaxies. So let's talk about what Webb has been expecting to do. As I mentioned, Webb is uniquely tuned to see the first galaxies in the universe. This is an image of one of the Candles fields of one of the Hubble Deep Field surveys. This image, up until a week ago, was of the oldest galaxy ever detected. I hate to break, break the tension so early, but Webb, there's already been a published paper about an earlier detection of a galaxy already within the first month of Webb. But this is a galaxy that was detected by Hubble from about 400 million years after the Big Bang. It is a small red faint splotch. In order to see galaxies that are earlier, we have to find things that are smaller, fainter, and redder. And as I mentioned, Webb is a giant telescope specifically designed large enough to capture enough light from galaxies that are fainter than this faint red splotch. And it is designed to capture things that are redder than this faint red splotch, which are infrared. Webb's first inception goal was to find the first galaxies in the universe, and we are well on our way. The first galaxies are a critical piece in the entire galactic evolution story, which is something that we have barely been able to piece together from deep fields. Shown here is a series, I believe actually Frank Summers put this together, from an animation of the Hubble Ultra Deep Field. But this is a sample of what we believe galaxy evolution could look like. Galaxies got more structured, they got larger, they got bluer over time, but that process isn't a straight line. There are a lot of mergers, collisions, changes in galaxy structure as this evolution has happened. And we really have only scratched the surface of understanding how these happen. And not just that, but what does it mean for the star formation within, for the black holes within, and for the overall composition and final state of these galaxies. So by being able to study galaxy fields very efficiently, deep fields of galaxies, Webb is able to get images of nearby galaxies, distant galaxies, young galaxies, old galaxies, all in one shot, and give us huge surveys of galaxies at different galactic evolutions to help us fully put together this picture of what does galactic evolution look like, and really fill in that early piece of what did the first galaxies look like. Because other than faint red splotches, we didn't have a lot of idea until now. Of personal interest to me is that we can study star and planet formation. Going back to the capabilities of near-infrared light to look through dust, we can look through very dusty areas where stars and planets are being formed, look through them to see those young stars, to study those young stars that were previously hidden at visible wavelengths. This is actually Hubble imagery that really just scratches the surface of what we were able to study. And Webb has much greater clarity and incredible spectroscopic capabilities to study what is in these star and planet forming environments. And that spectroscopic capability really comes into studying the makeup, not just finding the stars behind this dust in these molecular clouds, in these stellar nurseries, but studying what's there using the incredible spectroscopic capabilities of Webb to study very interesting molecules, as I mentioned, that just happen to emit fluoresce at these wavelengths. Webb will be able to study our solar system. You may have seen a very cool image of Jupiter that was taken during commissioning testing. And that's just scratching the surface because that was taken as a commissioning test, not as actual science data. But there are lots of programs within the first year to study all four of the giant planets, also Mars, also the Kuiper Belt, also, I believe, the asteroid belt, but definitely the moons of the giant planets as well. You can see here that atmospheric patterns in the giant planets really come to life. And we're also studying the molecular makeup of these as well. Infrared light is heat, as we said, and it is especially tuned to the heat of young hot planets. So the Earth is at about 6,000 degrees Kelvin, or sorry, the sun is at about 6,000 degrees Kelvin. The Earth is at about 300 degrees Kelvin. Webb can look at things that are about as hot as the Earth and slightly hotter, which includes exoplanets that are pretty close into their star, what we call hot Jupiters, which we know there are a lot of. Webb can actually detect the heat from those hot Jupiters and do what we call a technique called direct imaging, where you block out the light from the central star using chronograph and directly see the heat signature from hot exoplanets. This is an example of a system called HR 8799. This was taken using ground-based data, the Keck Observatory, but Webb has this capability and will study systems like that and will probably discover new planets using this technique that is uniquely an infrared capability, because that is where those planets emit the most strongly. That's where their heat signature lies, at infrared wavelengths. And finally, but definitely not least, is studying exoplanet atmospheres. Shown here is what we call a spectra, which I've alluded to. The process of spectroscopy is collecting a spectra, collecting light that has been split from one single light color into many, many colors, or what we call wavelengths. Wavelength is just a proxy for color, or color is a proxy for wavelength. You can consider all of these different wavelengths. And this is a spectra of what we would expect the Earth to look like, where you see features like water, ozone, carbon dioxide, methane, very interesting molecules that we associate with life on Earth, and that are very prominent in emission at infrared wavelengths. Infrared wavelengths are the area of the electromagnetic spectrum that you want to study if you want to assess the habitability or the appearance of the signature of organic molecules in extrasolar planets, or in stellar nurseries, or planetary nebula, any astronomical object. If you look at infrared wavelengths, that's where you're going to see these really interesting molecules like carbon dioxide, like water, like methane, things that we, in our anthropomorphic view, associate with life, but that are very abundant and interesting and chemically reactive, even if we're not looking at life. So, in the interest of time, let's get down to business. I'm sure you've all seen these before, so it's not quite the big reveal, but it is amazing to talk about what Webb was supposed to do, what it could have done, and then actually look at what it did. And this was just the first shot. So the first image that was revealed for James Webb by President Biden was what we call Webb's first deep field. It's an image of the lensing galaxy cluster SMACS 0723. And in this image that only took a matter of hours, now mind you, the Hubble deep field and the ultra deep field and the extreme deep field and all of the deep field surveys that have been done have been on the order of days or weeks. This image, each filter of this image only took 2 hours. And we found a galaxy in this image off the bat that was over 13 billion years old. I'm at a loss for words because I was at a loss for words when we first found this. It is stunning, it is mind-blowing, and it is just scratching the surface of what Webb can do. There are hundreds, if not thousands of galaxies, I'm not gonna lie, I haven't sat down and counted by myself, in this image. And the understanding that Webb has given us in 2 hours of a filter of the universe is mind-blowing. The other amazing thing that's not in here, but you can see in our press releases from July 12th, is that not only do we get this beautiful image, but we can actually, because of how big and powerful and precise Webb is, we can actually not just see that galaxy that is 13.1 billion years old, but we can tell you what is in it. And this enables that study of galaxies over time from not just a morphological perspective, but from a chemical and much deeper understanding. I'm telling you, when we first got this data, I was sitting in the room with a bunch of astronomers. I myself am not a galaxy person or a cosmologist, but the people who study galaxies, when we first saw the spectra, very, very easy to gather from a 13 billion year old galaxy, they were almost crying. Speaking of spectra, the next thing that was released from Webb was the spectra of an exoplanet. Again, just scratching the surface of what Webb will do for exoplanets. What's really interesting about this planet, WASP 96b, and you can see here that Webb has detected a signature of water in the atmosphere, is that it's not just water. And as you can see, the model matches the data, but it's not exactly precise. And that's because the Webb data has confirmed the existence of clouds and haze in a water-dominated atmosphere of this planet. But it also shows us that there are improvements to the model that need to be made in order to accurately reflect the data. That's what precision data, that's what Webb is going to do for us. It's not just give us data, but it's going to improve the models that are modeling the data. And so there's this positive feedback loop where really good technology informs and observations inform theory, and then theory models observations. And as scientists, we keep pushing the limits in that way. But in one transit of an exoplanet, Webb has proven that it has incredible stability, precision, and can teach us new things about exoplanets. The Southern Ring Nebula is an example of a planetary nebula, which is the death of a lower mass star. And as the star dies and burns successive layers of its material, it sheds its shell. It sheds material, it gets blown out. You may have heard of a supernova, but this is a smaller version called the planetary nebula. And you see, with Webb's clarity, you see the actual morphology, the actual shape and structure of this ejected material. It's quite unique, this system is, because it's actually a binary system. There are two stars at the center orbiting each other. One of them has died. And so the gravity from the other star has influenced the shape of this nebula. But using the clarity that Webb provides us at near-infrared wavelengths and the additional detail at mid-infrared wavelengths, we can study the dynamics of this system, of how the star died, how the gravitational interaction between these two stars impacted that. And I mean, it's just stunning also, this picture. So in addition to studying where stars are born and the environments in which they're being born, by being able to see through nebula, we can see what happens when stars die and study both the physical processes and also the chemical makeup of these ejecta to understand the full stellar life cycle process, in addition to the study of galaxy evolution. Speaking of galaxy evolution, as I mentioned, one of the key things that happens in a galaxy's lifetime is mergers, interactions with other galaxies, as shown here in this system called Stephan's quintet. What's really interesting here is this red part in the middle of these top galaxies that is the dust that is highlighted, whose heat we are seeing, the dust from these interacting galaxies that have been merging and interacting. And you can see one at the top and sort of two at the bottom that have interfaced, and you can see where the dust has been smeared out as they gravitationally interacted. I like to call this the dragon. And if you look at the mid-infrared image that was published, it's very bejeweled tones, and it's very beautiful. It's like a dragon hoarding its jewels. But again, the clarity here of looking at these galaxy interactions, studying the dust, and very complementary to what Hubble sees when it looks at interacting galaxies, is going to provide a wealth of information to what is happening in these systems. And then finally, but not finally, because it is my absolute favorite image ever, is the Carina Nebula. This star-forming region really shows us the capabilities both of infrared and near-infrared and mid-infrared wavelengths, where you can see stars coming through this nebula, but you also see the rich structure of this star-forming region, of this area that is just teeming with nascent stars and planets. And using the combination of these different wavelengths, we can study the material that's there, and we can look into that material to see what's inside as these stars and planets are forming. There's so many things in this image and it's such a high resolution, detailed image, thanks to Webb's capabilities, that it is hard to know what to talk about, but there are new structures here that I think are going to require new science explanations. For example, this thing sort of in the middle, lower center left that looks like a crane, like a swan craning its neck. Who knows? We can't explain those just from what we know right now. And so just this image alone is going to push astronomers to figure out new phenomenon. I love this image. And finally, I would be remiss if I didn't very briefly mention the result that came out just today of the Cartwheel Galaxy. This was an iconic target that Hubble looked at many years ago, and that's shown here on the left. And Webb looked at it and saw something the same and different. I think the two biggest striking differences to me are, one, the vibrancy of the dust lanes in the spiral galaxy, which is exactly what Webb mid-infrared wavelengths are good at highlighting, is that dust coming through. So we're not just seeing stars and hot gas, we're seeing the dust structure, the dust lanes of the spiral galaxy. But also the galaxies in the background. Webb is so powerful that it just can't not see 100 galaxies everywhere it looks. So please go back, and if you haven't seen this on today's news, it was just released this morning as the latest imagery from Webb. And we do expect to have new results from Webb every 2 to 3 weeks from here on out. And there should be new scientific results, peer-reviewed scientific results coming out very shortly, definitely this fall. So stay tuned, because as we've talked about what Webb could do and what it has done already, and by already I mean in the past 3 weeks, of what is surely to be a beautiful decade-long, if not more, mission, the impact on every aspect of astronomy, from the early universe to our nearest neighbors in our solar system, is going to be mind-blowing. And so with that, I will take questions. Thank you.
All right, Alex, thank you very much for that. That was a great overview, not only of the history that led up to these amazing new observations, but a showcase of the Webb's first images and spectra. And of course, we always want to notate spectra, because a lot of the infrared science will be done with these amazing spectra. Did you know what percentage of Webb's observations will be images versus spectra?
Yeah, that's a great question. And the number is, I think, 76% of the first year of science is spectroscopic observations. So while we love beautiful images, astronomers really appreciate the fact that when you break down light into its component wavelengths or colors, you get the most information, like what is there and how fast is it moving and how far away it is. All of that information can be gleaned from a spectra. And all of that is extremely valuable in understanding these phenomena. Right.
Yeah. So much of the physics of the object shows up in the spectra, and instead of just the images. Although, you got to keep them happy with the images, so you're going to have to keep pumping those out every few weeks, right?
Yes, they will not go anywhere, and as we've seen, they do not disappoint.
Okay. Why don't you stop your screen share?
Okay.
I have one question that came up in the chat that I wanted to ask you first. So you mentioned that you've got 20 years of fuel for station keeping. All right. So it can do its librating orbit around the L2 point for about 20 years, which I think is amazing, because I think the spec on that was 5 to 10 years, right?
Mm-hmm.
What are there other limitations to the lifetime of Webb besides that station keeping?
So yes, that's a good question. And, I would lie if I said, no, we're just gonna, it's unlimited.
Well, we didn't think we'd get 30 years out of Hubble either, but we'll see.
That's true. But Hubble is and has been serviced.
Right.
So the instruments on Hubble have been repaired, replaced several times. So that's a key factor, is that, electronics fail. Your cell phone only works a couple of years. I mean, whether or not that's given by the company, but electronics naturally, they have a limited lifetime. And so unfortunately, that is the case for Webb instrumentation. So we're not, I can't promise, none of these have been spec'd. None of the instruments, were built or promised for a 20-year lifespan.
Mm-hmm.
They were for a 5 to 10-year lifespan. And if any one of them fails, the other 3 will still work. So there's a lot of longevity there. And the other thing that has come up even recently already for the telescope is the impact of micrometeorites. Fortunately, both the sun shield and the mirrors were designed to really be quite robust against micrometeorites. The sun shield is designed with this sort of knit pattern so that if any object breaks the sun shield at a point, it only propagates a very small distance. And so it doesn't rip the whole thing. It just rips a very small space, which really maintains, the thermal capacity of the sun shield. And a few weeks ago, there was a rather largest micrometeorite impact on the main mirrors. And as you can see, it's still doing really great. Webb was very intentionally made, knowing that it was going to face the extremes of the space environment.
Right.
The 18 mirror segments can be individually moved to refocus the telescope very well. So even if there is a ding to one of the segments, or 1 or 2 segments go offline completely, the entire telescope can still refocus and work beautifully. So there are potential limitations to the lifetime, but it's hard to say, if and when any of those will become significant.
Cosmic ray hits are unpredictable, right? They're random. And Hubble's had its share of cosmic ray hits, and I'm sure Webb will have its share too.
Yeah.
Let's just hope that they push off way into the future. Okay. All right. Grant, why don't you join us? I'm looking over here to my left at my laptop, and I'm seeing lots of questions in the chat coming up now that the talk is over. So, Grant, why don't you turn on your video and come on and pull up some of the questions you found from the chat.
Absolutely. Thank you for such a good talk so far, Alex. There've been questions all throughout the chat. So let's get us started. What makes James Webb able to study such bright objects without saturating the detectors? Give you a chance to talk about microshutters a little.
Well, there is microshutters as well. So Webb does have the ability to pick and choose very disparate sources of the sky, thanks to a very precise and elaborate thing called a microshutter array. But I think in terms of brightness, there actually was concern that a few things in our solar system might be too bright for Webb. You're really only talking about things like maybe Mars, Jupiter, Saturn, because they're big and close by. But it's been handled. I don't actually know why it.
Well, I mean, it's a matter of exposure time, right? You can set with Hubble, we have they sort of have the problem in that you've got the orbit around Earth that sort of sets sort of a typical exposure time, but Webb doesn't have that problem. Webb is free floating. Well, it has its orbit, but that's a month orbit, so that doesn't really affect anything. So you can really set the exposure time like you would an SLR camera. You can set the exposure for longer or shorter. And if it's a brighter object, you take the shorter exposure.
Mhm.
Yeah, I can't imagine Webb having a minimum exposure that would saturate with Jupiter. We've already seen Jupiter, right?
Yeah, yeah, and the specs for Webb were to be able to study Jupiter.
Yep.
So, when they originally planned it, they weren't going to plan something that was so sensitive that was just going to.
Yeah, and I was very glad that the Webb mission released that image of Jupiter, because there was a question in the chat like, well, can it study planets too or anything? Because Webb is a general purpose observatory, planets, stars, nebulae, galaxies, all the way to the edge of the universe.
And it's passed all of the moving target tests. So moving target acquisition, making sure that it can follow things in our solar system, which move very fast relative to the background, because they're nearby. So
cool. So we'll be able to get some asteroid and comet shots.
And that leads us directly into our next one, which is, could you explain the difference in the diffraction spikes that we see between, let me get to that, James Webb and Hubble?
Yes, in short, the very cool snowflake looking Webb diffraction pattern is a result both of the shape of the primary mirror, the hexagonal shape versus Hubble's circle, and the fact that the geometry of the optics includes a secondary mirror on a tripod strut thing. So I can't do it justice. If you go to webbtelescope.org and look at the infographics there is a really cool infographic that beautifully, very cleanly explains exactly how we get this 6+2 kind of pattern, diffraction pattern, based on the physics and geometry of the optical system.
Right, but it's a great way for folks to be able to sit there and go, that's a Hubble image, that's a Webb image. Okay.
Yeah, yeah.
I think that's really good because it's pretty clear once you see the diffraction spikes. All right, what next we got, Grant?
Sure. When you were talking before, you referenced water detection with WASP 96b. What do you mean when you say water detection? Is it atmospheric? Is it actual, like, not you, is it actual water that is on the surface of the planet, or is it what's detected in the atmosphere?
So that's a good question. When we study exoplanets, we generally study the upper parts of their atmosphere. In this case, this is a detection of an exoplanet passing in front of a star, and the light from the star actually goes through the atmosphere of the planet. And as the light from the star goes through the atmosphere of the planet, light waves get absorbed. And by looking at the spectra, we can tell that those absorbed light waves coincide with what water vapor would absorb. And so we're detecting water vapor in the atmosphere, and really in the upper atmosphere, mostly of the exoplanet.
Right, and it's important, of course, to get the infrared infrared observations, because there's so many of the water and carbon dioxide and methane lines in the infrared that you don't see in the visible light.
Exactly.
Awesome. This is actually an interesting one. So Webb is designed to look for galaxies further away, but it sees IR wavelengths shorter than Spitzer. Why wasn't Spitzer able to observe some of the same things that Webb was? Yeah. Detectors.
Webb is about 50 times bigger than Spitzer. That's all.
Yeah.
That's
The resolution of a 0.8 meter telescope versus a 6.5 meter telescope gives it that ability.
and the light collecting tower.
Yeah. Oh, and the light collecting.
Both of them.
I think I've been impressed by the efficiency of Webb. When they showed that the systems on Webb are 10% above spec, and just obviously from the first images that you're showing how deep you're getting in just these short exposures. that has really been impressive.
Yeah. Yeah, when you send something, that's so expensive up into space, and time really is its currency, to know that it can do such good science in a very small amount of time. Just, even if it doesn't last for 30 years, the efficiency with which it can do science means that its scientific potential is, as good as Hubble's, maybe, hopefully.
Oh, definitely.
And I believe we have said this on the channel before, but it bears repeating. What was the difference in observation time between the Hubble Deep Field and the Webb Deep Field, just to give people an idea of how much that scale is?
Yeah, that's a good comment, and it's not really fair, the things that have been put out on the internet right now of comparing the S-max field, because the S-max field was not a deep observation that people have been showing of the Hubble observation of that same field. So it's not really apples and apples, but a Hubble Deep Field, for example, the Hubble Deep Field was, I think, 87 hours of exposure time. And the Webb one was 12 total for near infrared and mid infrared. So it's really almost a factor of 10 difference to get the same depth.
It's mind-blowing.
Yeah, and one of the really cool things about this is that, even in, say, the Planetary Nebula image or the Stephan's Quintet image, that there are tremendous numbers of background galaxies that show up because they're just show up brighter. And once you redshift those galaxies, they're in the infrared and they show up so much more, so much brighter. And, there's just a tremendous number of background galaxies, even in images that aren't meant to be deep fields.
Yeah.
That actually leads right into the next one, which is in the image of the Carina Nebula, someone noticed that they were able to see what looked like stars either in the actual Oort cloud or just behind that observation. And that's one of the things that JWST is able to do, being infrared. So would you expand a little bit more about the ability to observe stars through or in the dust?
Yeah, so this is one of the coolest demos I've ever seen. Is if you hold a trash bag up to an infrared camera, you can actually see right through the trash bag. So our eyes can't see it through a trash bag, but an infrared camera can. That's kind of the same thing with stars, is that our eyes can't see through the dust. It's basically like put a giant trash bag in front of your face. But with an infrared camera, bam, you can see right through. Alternatively, what's really interesting is that if you hold a piece of glass up to an infrared camera, you can see right through it. The infrared camera can't see squat. So it's really different wavelengths see through different materials. And so here, so in an image where it just looks like dark lanes of dust, Webb just sees right through it to the other side, or depending on what the opacity is and the exact wavelength, can see kind of to the middle. So yes, there are a lot of stars here and new stars that we've never seen before in this image of the Carina Nebula, thanks to the depth that near infrared wavelengths give us into this material.
I like this one. Since JWST is in motion, obviously it has a short elliptical orbit of its own. Does that produce any noticeable Doppler effects?
That's a good question. If I don't think so. I mean, it's a legitimate question, but they would all be calibrated out in the processing software, so we haven't seen any.
Yeah, Hubble's moving at 17,000 miles per hour, right? So we've been able to do this quite well for 32 years. We can handle it for Webb too.
Yeah, the Earth is moving.
Yeah, the Earth is moving. The telescopes are moving. We've got all that taken care of. So that's a solved problem.
So we did touch on this a little bit, or you did in your talk, but knowing that there's really only one finite resource on Webb, which is I believe it's the station keeping thrusters, correct? Just to keep it in orbital position. what do we have an idea for an expected life versus a possible life for the Webb mission?
I would say we're basically expecting 10 years now. A good 10 years.
Let's be conservative at this point.
Yeah.
We've only got a few months worth of experience operating this telescope, but if everything keeps going like this, it could be really great, but we have to be conservative.
All right. So what determines what Webb is going to observe? We've talked about this on the channel before, as far as like discretionary time from the director, which is how we got the first deep fields, and obviously like double-blind proposals. But could you talk a little bit about that?
Yeah, that's a really good question. And actually, that's a lot of the bread and butter of the work of the Space Telescope Science Institute, is figuring out what Webb and Hubble will look at. And it is not a it's not really our choice, but instead we run processes, very rigorous selection processes. So what happens is every year we put out a call to anyone, but generally is responded to by astronomers across the world, to say, I would like to use your telescope, Hubble or Webb, and I would like to look at this thing for this reason and this number of hours. And Space Telescope Science Institute gathers a group of astronomers to rigorously evaluate those proposals and say, these are the most valuable ones in terms of the science that they will deliver. So this is what they should look at. So most of the time on Webb over the next decade will be chosen by a peer-reviewed process. Some of the time, especially in the next year or two, has been promised to certain astronomers who have spent decades themselves working for Webb. So people who created some of the original science goals, some of the science instruments. So they've given years of their life to Webb, and in return, they get some guaranteed time. As well as you mentioned, the director of the Space Telescope Science Institute, in his position, gets some sort of guaranteed time of his own to make sure that there's other opportunities that don't get missed for the telescopes.
What kind of capability?
And I just wanted to comment on that, because what you recognize is that when we run these telescope assignment committees, we bring in hundreds of astronomers to do the evaluation, and that only about 10% of the proposals actually make it through. So I mean, the amount of people who want to use Hubble and Webb is always going to be much greater than we have time available. So it's something that this is a very valuable resource, and that we make sure that only the best science qualifies.
All right. So let's move on. There was a question about the Lagrange point. So talked a little bit about the orbit already, but what exactly is the Lagrange point, and why was it chosen for Webb to be more or less stationary there for its observations?
Yeah, so just briefly, that's a good question. And I didn't explain this as well as I could have. A Lagrange point, and in this case, the second Lagrange point, there are 5 Lagrange points for any sort of two bodies orbiting each other. There's 5 points around those bodies where the gravity of those two bodies kind of cancels each other out, for lack of a better term. And so it means you can kind of hang out there. And so one of them is this place, the second Lagrange point. And of all of the points that you can kind of hang out around Earth and the sun, the second Lagrange point is one where you're on the same side of the Earth and the sun at all times. So in short, that's why we chose it. You can read a lot more about Lagrange points and how they come up in orbital dynamics online, but it means that we don't have to carry a lot of fuel, we don't have to use a lot of fuel, and we can always keep our precious telescope in the shade of the sun shield.
Okay, Grant, I'm going to jump in here because we only have time for one more question. And it's a question that always comes up. Is James Webb going to be able to detect life on another planet? That's one of the questions that always comes.
Yes. No.
You know, we're going to we get that question all the time.
Yeah. I mean, and you know,
what are the prospects?
Webb is a very important piece of, you know, NASA's and all, dare I say, humanity's, you know, looking for life out there. Webb is able to detect atmospheres of smaller planets approaching the size of the Earth, that we've never been able to detect before because they were too good. The atmospheric signature was too small, too faint. And we haven't had this capability at infrared wavelengths before, where we said very interesting things like methane, carbon dioxide, water hang out. So Webb is going to be able to detect atmospheres of much smaller planets than previously done at areas of the electromagnetic spectrum that are very interesting for habitability studies. So that's the step that Webb does. Webb says, hey, we found some cool stuff on some things that may have a rocky surface. There's a lot of steps to go from there to find life, but it's a fun start.
Yeah. You know, I think, you know, the major question for that is, what if there were a signature of biological processes in the atmosphere? What is that? Have we defined that well enough to be able to tell it, even if we did see it? So
exactly.
It's, you know, our detectors are improving, but also the other side of the equation has to improve enough so that we can say, yes, this is an undeniable signature, because, you know, the universe works in so many different ways that,
I mean,
really,
even our Earth, you know, the life forms we found on our Earth have defied our expectations as we keep looking. So
exactly. So Mother Nature is very, very inventive, and an undeniable signature. I'm not sure we know what that is just yet. Okay. All right, Alex, thank you so much for this introduction to Webb. Folks, we're going to be hearing a lot more about Webb over the next months and years. Stay tuned. It's going to be exciting. Next month, however, we will not hear about Webb. Well, we'll hear about something that approaches one of the Webb science topics. First Light, unveiling the properties of galaxies at cosmic dawn, which is one of those science things that Webb will work on, from Guido Roberts Borsani. We'll see you then on September 6th. Until then, thank you and have a great day.
bye. Thank you.